Hello everyone. Today let's solve the problem number 1448. Count good nodes in binary tree. So you can just go through the question and you can just go through the examples as well so that you can understand the question pretty well. So I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given a binary tree and we need to find the good nodes in it. So we are given a binary tree, you can clearly see. So we need to find the good nodes in it. So what is good nodes then? A node X is called good if the path from root to X, there is no node with a value greater than X. So they have clearly mentioned here a node X is called good if in the path from the root to X, there is no node with a value greater than X. So let's consider the example 1 so that this question becomes easier to understand. So suppose if you are considering the path this one 3 to 4. First let's consider the root node. Suppose if we have only root node, let's consider 3 here. This is 3. So root node is always considered good. That's what they have given in the question. So root node, this is always good. So we are adding 3 here to the output. So this is one thing. And let's consider one more path, 3 and 4 next. So 4 is greater than 3. So this should be greater than the element that we are considering, right? So then only it is said to be good. Here 3, 4, we'll be adding 4 here because 4 is greater than 3. Let's consider this path 3, 4, 5 now. So this is also we are considering, right? 3, 4, 5, 5 is greater than 4. In this case we are considering 3, 4, 5 and 5 is greater here, right? So we will add 5. So this is one thing. Next, we have already considered 3, 4, 5. Now let's consider 3, 4, 1. So within this 4 is greater and 4 we have already considered here. So let's ignore this one. Let's come here 3 and 1. So 3 we have already considered here, the root node 3, right? So 1 is lesser than 3. So we'll ignore this one and let's move with the path this one 3, 1 and 3. So now we have 3, right? 3, let's consider 3 in this case. 3 is greater when it comes to this one, this path, if we consider 3, 1, 3, right? So the number of elements that is present here is 4. That's what the output here. They have stated the output as 4. So let's consider the next example. So just give me a second here. Let's consider the next example or the second example here. So here they have given 3, 3, 3, 3 null, 4, 2, right? And this one root. So let's consider 3. Let's consider 3 initially, root node, and 3, 3. Yeah, we can consider 3, 3. So it will be having now 3, 3. Because 3 is equal or greater than 3, right? So we are considering these two. Next, let's consider 3, 3, 4. So 4 is greater than 3. We'll be pushing this one, 4. So it will be 3, 3, 4. Now we have 3 elements, right? So let's consider 3, 3, 2 here. And we know that 2 is lesser than 3, right? So we will ignore this part. And we will consider these 3 elements. So number of elements present here is 3. So that's what we'll be displaying in the output here. So I hope the question is completely clear. I hope the example they have mentioned is completely clear. Let's move with the last example. We have only one element that will be considered as good. So we know that a root element, or if we have one element, it is considered as good. So here they have clearly mentioned in the explanation. Root is considered as good. So output will be one element. We have only one element, right? So the output will be 1 in this case. So I hope the question is completely clear. Let's discuss the approach followed by this one, edge cases, and then let's write the code and discuss the complexities of the code that we have written. So initially, as usual, let's discuss the approach. Sorry. So let's discuss the approach here. We'll be making use of the DFS, depth first search. So just give me a second here. We will be making use of the DFS or depth first search to solve this problem. So what is the first step here? We are maintaining a variable max so far. You can give any variable name. that is related to the problem. In my case, I'll just consider here max so far. Max so far. So we have why max so far I'm considering here. We for particular path we need to find whether the node is good or not, right? So for particular length we have to find the maximum value, and then only if we are considering these two nodes. So this one is this one second element should be greater than the first element. So that is the reason I have considered the variable name max so far. We have to do the same thing for every path, right? Here 3 4 3 4 5 3 4 1 3 1 3 1 3. So for every path we have to do. So this is one thing. Maintain a variable max so far to track the maximum value from root to current node, right? In this case 3 4 3 and 4, right? So here I hope this is clear. First step. Second step is if the current node value is greater than or equal to max so far, then it is said to be good node. So this one 3 and 4 let's consider here. I'm just considering only 3 and 4 here. Suppose initially this is the current node. This we are calling current node. Then this one we are considering max so far. So max so far, this one node's value, this one has to be greater than the value that should be that we have considered second one. This one has to be greater than the current node, greater than or equal to the current node, greater than or equal to the current node. So max so far initially was this one 3. This one was current node and max so far. Next element we are considering this one as max so far, right? So this element has to be greater than or equal to this node to consider this one as maximum element. So that's what we'll be checking. If the current node's value is greater than or equal to max so far, then it is said to be good node. I hope this example is completely clear. Next, we have we'll be making use of the recursion or recur for left and right subtrees, updating the max so far as this one. We can just write in this way. Just give me a second here. We are just recurring for left and right subtrees, updating the max so far as max of max so far, common value of the node. In this way we can just give, right? So I hope this is clear. These are the 3 steps that we need to this one keep in mind. So this is the approach that we are going with. So next let's discuss the edge cases one by one. Then after discussing the edge cases, let's write the code. So let's discuss the edge cases one by one. First thing is let's first edge case, let's go with the single node tree. So this one single node tree right here. This is fine. Input, let me consider here. We have to have only single node, right? I'll just consider here 1. So output will be 1 as well. We know the root is always good, right? So that's why the output will be 1. I hope this is clear. Next, let's move on with the second edge case. Nothing but all nodes have same value. So I'll just come here. Let's write all nodes have same value. When I say all nodes have same value, let me consider here root 5. This is fine. Root, this one I have considered. Output will be 5 in this case. Why the output will be 5? Every node is good here because no node has greater value in its path, right? So it has to be while explaining the approach I have said the current node has to be greater than or equal to the maximum that has been found so far, maximum element that has been present so far. So this satisfies the condition. So the output will be 5 here. So every node is good because no node has greater value in its path. So I hope the second edge case is completely clear. Now let's move on with the third edge case, nothing but strictly decreasing order. This one strictly decreasing order. When I say strictly decreasing order, so let me consider the input here root 5 4 3 2 1. So we have strictly decreasing order. We are considering the elements in the decreasing order, right? So the output will be 5 here in this case as well, because every node is good here. Since there is no larger value in its path at all, every node is good here. So the output will be 5 in this case. Let's move on with the fourth edge case, nothing but tree with negative values. So I'll just consider here tree with negative value, right? So in this case, let me consider the input root -1, -2, -3, -4, -5. This is fine. Tree with the negative values we are considering, right? Output will be 5 here. So why the output here 5? Why the output here is 5? Because even if the values are negative, we'll be checking based on the maximum value that has been present in the path. Maximum value is this one, right? -1. So initially, so even if the values are negative, we are checking based on the maximum value in the path. So the output will be quite obviously 5 here in this case. So I hope all the edge cases are clear. First one we saw for the single node tree. Second one we saw for the all nodes have same value. Third one we saw for strictly decreasing order. Fourth one we saw for tree with negative value. So I hope all the edge cases are clear. Next, let's start writing the code. So let's start writing the code. Initially what we will do, let's consider the helper function dfs. I'll just give here dfs. As we had discussed in the approach, let's go with the two parameters. One is node and max so far. So this is fine. Base case, what we had discussed in the approach, if the node is null, then we have to return 0, right? So in this case, if node is null, then we will just return 0. So you can just give node, you can just compare node with null as well. If not of node, return 0. In this way also we can articulate this one in the form of code. So this is the base case. Next, let's initialize count to 0 as we need this one. Finally, we have to count the number of elements when we compare these two nodes, right? Or when we compare the elements within a particular length, we need to finally display that one in the form of count itself, right? So let's initialize count to 0 here. The next step is if value of the node is greater than or equal to maximum that has been found so far, then count equals 1. So this is called as a good node. That is the reason we'll be giving count equals 1. In this way, we can write here, if value of the node is greater than or equal to max so far, then we can just give here count equals 1. So this is nothing but this node is a good one. So that's what we are writing here. So the next step is, so we have to update the maximum value in the path that we are checking for, right? So I'll just consider here max so far. So we have to update the max value, right? For that reason, I'll just consider here math.max of max so far. Let me copy this one, max so far, as well as this one, value of the node. This is fine. I hope this is clear. We are just updating the maximum value in the path. So next step is we have to recursively call the left and right subtree. So again, I'm telling we have to recursively call the left and right subtree. So here count will be what we are doing, count plus DFSO, this one, node dot left and max so far. In that way we can write, right? So I just give you a count equals count plus DFS of node dot left, comma max so far. This is fine. Same goes with this line as well. Instead of left, we are recursively calling for the right subtree. So this is fine. Node dot right. This is the only thing I have to change, right? So this is fine. Final step is we have to return the total count of good nodes that is found in the subtree. So in this case, we just have to return count. So I hope this is clear. So finally, we have to start DFS from the root node, right? So I'll just give here written DFS. We are starting from the root node, and we have to consider the value of the root. So I'll just give here root dot val. Hope this is completely clear. Let me format the code once and let me hit the run button. So what happened here? Oh, why this is not showing? Yeah, this is fine. So here you can clearly see all the test cases are getting, all this sample test cases are getting passed. Let me hit the submit now. So here you can clearly see all the test cases are getting passed. So the code works absolutely correct. So let's quickly discuss the time complexity and the space complexity of the code that we have written. So the approach that we went with here is DFS, or the depth first search. So the overall time complexity here would be big O of n. So why the time complexity here is big O of n? Because we are traversing each node exactly once. We are traversing each node once, where n is nothing but the number of nodes, we know that. So with the overall time complexity here would be big of n. So what will be the space complexity here? The overall space complexity here would be big O of h. Why the space complexity here would be big O of h? Because h is nothing but the height of the tree, we know that. In worst case, for the skip tree, if we are considering skip tree, for the worst case it would be time complexity would be big of n. For the balanced trees, it would it would be big of log n. So we can just consider this one h, nothing but the height of the tree for the space complexity, right? So the overall space complexity would be big of h. So here overall time complexity would be big of n and the space complexity would be big of h. I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.